All right, I'm finally back after hours. And so we are going to talk about Newton's second law a little bit more when we do more of the practice problems. But one thing you do need to understand are the units for force or weight. So force units and weight units are the same. Now, a lot of people, like if you use a scale, you weigh something, it weighs something in grams, you say, oh, its weight is 50 grams. But that's not actually the case. Its mass is 50 grams. Mass, as you know, is a quantity that doesn't change based on gravity or where you are. Your mass is the same on Earth as it is on the moon, as it is in the depths of space. You have mass, the amount of stuff that's in you. But your weight changes based on gravity. Because, of course, of Newton's second law, force equals mass times acceleration. So those grams times your acceleration, which gives you units of mass unit, we'll say kilogram, and acceleration is measured in meter per second squared. Well, a kilogram meter per second squared, that unit, since it's so unwieldy, we just call a Newton, named after Sir Isaac Newton, of course. So the force or weight unit is a Newton. So if, say, you weigh, I don't know, 100 kilograms, and we'll say, let's say all three figures are significant there, then that would be your mass. But your weight would actually be times 9.8 meters per second squared on Earth. It would be different if you were on the moon or in space or whatever. So 100 times 9.8, 980, we can only keep two significant figures, newtons. So you have to make sure that anytime you need to use force or weight, you're in newtons. Anytime you need to use mass, you would be in kilograms or grams, or something like that. Now there are other, possibly less commonly used in physics, ways to measure force or weight or mass. So here's our list. Make sure you know these. There's a little question on the test about this. So a Newton is a kilogram meter, that's a multiplying sign there, per second squared. A dyne is another force unit. It's for measuring very, very small forces, such as might be found in electronics where tiny little things are touching each other. This is the gram centimeter per second squared. But again, you see you have a mass unit times a distance unit divided by a time squared unit. Always going to be the case there, even if you change the different types of measurement. And then for English unit, the pound is our force unit, and that is the slug, which is actually our mass unit. So if I weigh X number of pounds, I could actually figure out my mass in slugs. So pounds isn't a mass unit. For us English folks, it's actually a force unit. So pounds are a slug times a foot per second squared. Once again, you have a mass unit times a distance divided by a time squared. So those are important to know. And for mass, I'll just change color here. These are our force units. Mass units would just either be the gram or some thing thereof, kilogram, centigram, or the slug if you're in English units. Those are the two mass units that we would use. I forgot to set my stopwatch so I don't run over on YouTube. Okay, so to convert here between weight and mass, just remember that weight is equal to mass times gravity, wherever you are. If you happen to be on the moon, of course, gravity is going to be different than the 9.8 meters per second squared it is on Earth, straight down. Force is a vector quantity. You must give a direction. Okay, a force goes in a direction. If I push in this direction, it's going in that direction. Okay, if I push in this direction, it's going down. If I push in this direction, it's going up. Force needs to have magnitude unit and direction. Mass is not a vector quantity. Mass is just a measurement of the amount of stuff in something, so it does not need, if you're just reporting mass in grams or kilograms or slugs, you don't have to have direction with mass. So, once again, lovely test question. What changes with gravity? Mass or weight? Okay, and of course you would say weight. Weight changes with gravity. Mass is the same. You're made of the same amount of stuff no matter where you are on the moon, on Earth, out in space. So Newton's third law then. Can anyone tell me what Newton's third law is? I hate not having a class to talk to. Alright, so Newton's third law, you probably have heard for every action there's an equal and opposite reaction. For physics we would say for every force there's an equal and opposite force. So just like I was trying to explain earlier about normal force, of course we know that the weight of the box or whatever this is a force, measured in Newton's. Weight is a force. There's always an equal and opposite force, the floor, say, pushing up on the object sitting upon the floor. So we know that the weight is acting upon the floor. The equal and opposite force isn't acting upon the floor, it's the floor acting upon the box. So when you look at Newton's third law, when for every force there's an equal and opposite force, the object that's receiving that equal and opposite force is different from the object that's imparting the opposing force. I know there's a test question that seems kind of confusing, which is why I'm giving you this big discussion about this. But let's say I wanted to scoot my easel over. I push against my easel, right? My easel pushes back against me. The reason that I can eventually cause the easel to move is because I can impart more force toward it eventually, if I push hard enough, then the easel can push toward me. That would be friction that's resisting the movement. So the test question I want to say is something like, you say, oh, I can't move the easel because there's always going to be an equal and opposite force. So I push on the easel and there's an equal and opposite force pushing on the easel, which makes it so I can't move it. But that's not the case. If you push on the easel, Newton's third law is equal and opposite force means the easel is pushing back on you. And you can eventually overcome the amount of force that the easel can oppose and cause it to move. So that's the basic point there about Newton's third law. I will read exactly what this says. With friction can oppose motion, so it will. It'll equal the force trying to move an object increasingly until a certain point. This depends on the surfaces and the mass of the object. And when we talk more about friction, which may be in about 2 seconds, I don't know how far I'm supposed to go today, then I'll describe exactly how friction works. So we went over Newton's 3 laws, mass and force units, even the weird ones like dimes and slugs, discuss kinetic and static frictional force. Oh, good. Okay, so my time. We're doing okay. So there are 2 kind of types of friction. There's static friction, static meaning obviously not moving, and there's kinetic friction, obviously moving. So remember how we talked about the things that cause friction to happen. Those little bumps and grooves, and if I can aim them right here, right, the little bumps and grooves. So when this object starts to slide on this surface, this little bump and this little groove and this little bump kind of crash into each other, partly causing friction. The other part is that little electrostatic forces in the 2 surfaces will attract and repel each other and cause some friction. What we see is when something is at rest, you have friction, which is greater than when 2 things are actually moving in relation to each other. So if these two, let's say this thing is a box and this thing is a tabletop. So let's say the box is at rest on top of the table in relation to the table. To get the box to start moving would require more force than to keep the box moving once it is moving. Because static friction is harder to overcome. These little grooves and bumps settle into each other, they get really close to each other. These little electrostatic attractions are able to really form tightly when the two surfaces are stationary in relation to each other. But if we got the box moving, then we'd be talking about kinetic friction, the friction between two objects that are moving in relationship to each other. In that case, these little electrostatic attractions would kind of zip past each other, not really be able to form. And the little bumps and grooves maybe would not settle in as much. Maybe they kind of just keep going right over top of each other. And the amount of friction that you would need to overcome to keep that box moving would not be as great as the amount of friction you would need to overcome to get the box moving in the first place. You'll see that in the experiment next week also, and we'll probably go over this exact same thing in class. Let's see. When your mother hits the brake in the car, why does she fling her arm out? Well, when the car starts to slow down very quickly, how about you? Do you start to slow down very quickly? No, because you haven't been acted upon by an outside force like the car has. So until the friction between your pants and the seat or the force of the seatbelt upon you begin to act upon you, you start to fly forward. Now, when I was a kid, we didn't actually wear seatbelts. Probably most of your parents didn't really wear seatbelts as a kid. So moms would fling out that arm to keep their kid from flying forward. Now, of course, we know in an accident, a person's mass times that acceleration would be much greater than the strength of a normal person's arm. But you can see that your mom is trying to stop you from moving forward, because even though the car is being affected by the brake, you are not. You have to be affected by something else, which we don't want to be the windshield. When you accelerate, why does everything, okay, so you're driving your car, why does everything in your trunk slide? So let's say we're sitting at rest at a stoplight. I have a big box of breakable lab equipment in the car. We can all see where this is going. I slam on the gas to get going after the light turns green. What happens to my box in my trunk, right? Well, my box is at rest in the trunk. The car is affected by a force, right? When I hit the gas, it starts to move forward. But the box is still at rest. So until friction causes it to begin to move with the car, perhaps there's not enough friction to begin to move it with the car, that box will stay where it is. The car will move and the box won't. So the box will move toward the back end of the car a bit. And that's why you don't want to accelerate too quickly when you have a lot of stuff in your car, and especially why, as new drivers, you guys really want to keep your car free of clutter. I'm not a person to talk here, but those things can become projectiles and be very unsafe, so do be careful about that. The same thing, if you put your beverage, and I had a driver's ed teacher who actually did this to make sure that we were driving carefully, put your nice hot beverage on the dash, and then you're driving along, and then suddenly you hit the brakes. Well, the car is affected by the brake, but the beverage is not. So the beverage, right, is going to continue to move, but the car is going to start to stop. So which direction is that beverage going to go in relation to the car? Well, it's going to, of course, fly forward or backward. So think about that. Here, your car is moving, your beverage is moving. Your car suddenly starts to stop, your beverage keeps moving, your beverage is going to tip. If you were to, say, accelerate very quickly, your car would speed up, your beverage maybe wouldn't, unless there was enough friction between it and the dashboard to keep it going. So your beverage would come toward you if you accelerate fast. Just things to think about, things that friction can do or maybe not do enough. Today's lab, I need to stop. Probably YouTube's going to hate me, so I'll be right back.